Now I want to apply the central limit theorem for proportions for p hat to some real life data. So according to a recent article, 98% of the people who travel on the New Jersey Turnpike exceed the 60-mile-per-hour speed limit. Well, yeah, 60 mile per hour is pretty slow for a turnpike, but okay. So law enforcement officials are planning to covertly, meaning secretly, measure the speed of 750 cars on the turnpike and will compute the proportion of drivers who exceed the posted speed limit. Okay. So we're going to describe the sampling distribution of p hat, the sample proportion of drivers who exceed the speed limit. We're going to give shape, center, spread, symbols, explanations, everything. All right, so let's look back at the central limit theorem. So the first thing is we need, well, let's note the conditions are met. Oop, 1 second. I pressed the wrong button. All right. So let's make a couple notes about those conditions, like I was just saying. We're going to say that the sample is safely assumed to be random and independent. I actually just added the word in random just to make really clear this is random. Now, independent's going to happen kind of automatically. And the reason that's going to happen is because um, if the cars, I mean, the cops are not actually coordinating from car to car which cars they zap. So it's actually possible to do this with replacement. It is possible for that same car to be radar gunned a couple times as it's traveling down because different cops might covertly measure it, right? So it's not even really without replacement. It's actually with replacement because the cars could be taken. You could have the same car drive down this road a couple times, and different policemen are out there measuring the speed, and they might measure the speed of that car a couple times. So it's got the random, it's got the independent, right? Because, one car speeding doesn't necessarily have a bearing on the other. We're just going to assume that that's true, even though one might argue that's not the case on the road, but we'll just leave it alone. And then N is 50, or 750, excuse me, because it says 750 random cars. And then the P is 0.98. That's your population assumed value. Assumed value for population proportion, I should say. Okay, so let's see. Can we prove the center, right? Well, if the center is going to be normal, we're going to need one more thing to prove. So we need to prove that n times p times 1 minus p is greater than 10. So n was 750 times p, which was 0.98, times 1 minus 0.98. So we need that value to be bigger than 10. So let me grab a calculator. 750. Oh, here, I'll make it a big screen so you can see it more easily. There we go. There. 750 times 0.98 parentheses 1. Oops, I lost my 8 there. 8 parentheses 1 minus 0.98. Close parentheses, enter. I get 14.7. And 14.7 is indeed larger than, which is greater than or equal to 10. So, yay. Right? So we've proven our 3 assumptions are met, right? So I guess I should say conditions, right? So we've met the 3 conditions right here. So we've got our random and independent. We've got n is 750, and then p is 0.98, and then there's our 3rd condition, that n times p times 1 minus p is greater than 10. All right, so now we know it's normal, right? Because the conditions above are met, right? You can't actually say it's normal unless you prove the conditions part first, right? Oh, sorry, that's not center, that's shape. I'm losing my mind. Sorry, that's shape. Normal. Now the center. There we go. And that will be the mean of the p hats, but that's automatically p, which is 0.98, according to the central limit theorem. Okay? Right there. And then our spread, well, that's the hardest part, right? Because we have to do a little calculation for that one. So the spread is the standard error of the p hats, and that's the sigma p hat. And I don't care which symbol you use. I actually use the SE symbol a lot because I find it easier. But, if you want to use the sigma p hat, that's fine, right? So it's sigma p hat, which is this square root p times 1 minus p. And I found it to be 0.005, but let me prove it to you again. So I want the square root p, which is 0.98, times, so a little time symbol, or you could just do parentheses, 1 minus 0.98, 0.98. There we go. I'm typing it, but I'm typing so fast the computer doesn't like it. And divide by 750, enter. I get 0.005112. And that's what I wrote right there. And just a little reminder, we want to keep at least 6 decimal places for standard error of p hat. It's just best for all involved that we keep more accuracy. Okay, so we proved the conditions, condition 1, condition 2, condition 3, and then we found the n and the p along the way. And then once we had those conditions, we know that these 3 things are true, right? The shape is normal, etc. Just to clear this up here at the top, I just kind of relabeled these. So condition 1, random, condition 2, independent, and then we proved condition 3 right here. And I put a little number 3, yay! So we met all 3. Once we know those 3, then we know the shape is normal, the center, and the spread. And we're all set from there. All right, now that we know that, let's look at a random sample of 750 drivers. So the same sample that we just found the distribution for right here. What is the probability that more than 98.5% of them are speeding? Okay, so we know that the center is 0.98, so we want 0.985, which is over on the right, and we want to shade more than, so we're going to shade to the right. Okay, so I already found this. Let me put it in 1 second. There we have it right here. So you take your normal curve. Now, obviously this is one from a computer program, but it's the same idea. You put 0.98 down the center. You put 0.985 over here. 0.98 is your mu. Put 985 here, and you're going to shade to the right. And when you're looking for this, what you're really looking for when you're looking for probability is the area, right? So you want to know the area that's over here to the right. In fact, I should shade it gray since that's what we're looking for. Okay, so you're going to do that with normal CDF. Now here's the thing. When you use normal CDF, you have to put in, so if I go to second distribution, number 2, normal CDF, right? And then I want to tell it 0.9985, and then 1E99, and then 0.98. Okay, now here's where it gets interesting. Now you could type 0.00, what was it, 5112 right there. So you could type 0.005112. So that's an option. You go down to paste and press enter. And press enter. Fine. But there's another way. When you do the normal CDF, what you can actually do is type the square root formula right in there. Square root 0.98 times, parentheses 1 minus 0.98, close parentheses, divided by 750, and finish off my parentheses right there. I technically don't need that time star in there, but I'm not going to go get rid of it now. Go down to paste and press enter, enter. And that's a tiny bit more accurate. That's why you see how they're different in the 6th decimal place or so. That's why I said to keep 6 decimal places. Because if you keep 6 decimal places for your standard error, then these 2 probabilities will basically be the same, right? For the first 4 or 5 decimal places, which is all you need for your answers, right? So we get 1640 right there. And if you round to less than 6 decimal places, then you're going to have wrong answers. So if you used 0.005, for example, let me just show you that real quick. So if I used 0.005, I go back here. Instead of 5112, if I used 005, that would have been my answer. Do you see how different that is from the real answer? So that's why I say keep at least 6 decimal places. That's why. Because if you don't, you will lose accuracy wicked fast, right? So be careful with that. And sometimes it's just simpler just to use the square root and be done with it. All right, now what about the 37th percentile? Well, that's going to be over on the left-hand side, right? Because remember, the median's the 50th percentile. So let's remind ourselves of a couple things. When we want to find percentiles, that means that we want to use inverse norm. 1 second. Let me go find you the decision matrix real quick, because I threw in a decision matrix at the end of chapter 8 for you. Right there. There it was. All right, so this one's the one for 8.2. There's another one for 8.1. So in this case, you want the percentile. So if you look over here, you want to find percentile. See it right there? Not percentile rank. That's this one. But you're looking for the percentile. And it says right here, use inverse norm, left area, p square root p times 1 minus p, blah, blah. So that's what we're going to do. So we're going to use inverse norm. Our p is 0.37, right? Or p hat, excuse me. So, and then our area, not p hat, I'm so sorry. So we're looking for p hat. Our area is 0.37, that's our left area. Our p, there it is 0.98, that's our middle value, the mu in the center. And then square root 0.98, 1 minus 0.98 over 750. So let me grab the calculator. I'm going to use inverse norm, which is number 3. My left area was 0.37 because that's the percentile I'm looking for. 0.98, 0.98, there we go. And then same as before, we could use the square root, 0.98, parentheses 1 minus 0.98, divided by 750. Go down to paste and press enter. And then press enter again, and you get 0.9783. So let's see how many decimal places they want. They want 4 decimal places. So that's why I said p hat is 0.9783 or 97.83%. It's going to be really high because, of course, remember your middle is 98%. These are proportions, right? So it's got to be a number smaller than 1, but bigger than 0. And it turned out to be 0.9783. That's because your spread is so very, very small. Your spread is only 0.005. Very tiny.